This is a tutorial on the basic concepts of electrochemistry, and to study this we will focus on the following chemical reaction here, where if we have a piece of solid copper in contact with a solution that contains sodium ions, you'll find that at the end of the reaction solid silver metal is formed and copper 2+ ions are formed in solution. Let's take a quick look at what this actually means. If we have a beaker, and in that beaker we put, say, a piece of copper wire in that solution, and let's say that we have the solution that contains some silver nitrate or some other form of soluble silver ions. After a while, what we would observe is the copper wire starts to get darker, and that's due to silver ion or silver metal precipitating onto the wire, and the solution around the copper wire, if we don't stir it, is going to start turning blue, and that blue is due to the copper ions going into being dissolved into solution. So if we take a look at what's going on here, we started off with copper ions, copper metal. Oops. Let me change my pen here. Get rid of that. And we start off with copper metal, and that copper metal is converted into copper ions. Notice how we go from an oxidation state of 0 to an oxidation state of 2+. Therefore, we have loss of electrons, and loss of electrons is an oxidation. Likewise, we have silver ions, this time gaining electrons to become silver metal, and gain of electrons is a reduction. So if we were to just summarize this to highlight some of the terminology that is used in electrochemistry, in this case here, our copper, which we said was oxidized, we said that our silver ions, notice how we are only looking at the reactants. We never refer to the products as being oxidized or reduced. These are features of the reactants. So, oops, was reduced. The copper ion, the copper metal, also served as the reducing agent, because it was the material that was doing the reducing. Another term for the reducing agent is the reductant. If the copper was the reducing agent, then we can presume that the silver ions were the oxidizing agents. And another term for that would be the oxidant. So these are terms that you need to know and need to be able to understand when they're used. Okay, let's talk about two concepts before we get to an example problem there. The first concept that I want to talk about is electric charge. Electric charge is measured in coulombs, and the abbreviation for coulombs is C, and the variable that we typically use for charge is the variable Q. Now, one electron has a charge of 1.60 0.02 times 10 to the minus 19 coulombs. And if we were to ask ourselves how much charge does a mole of electrons carry, we would simply take this number above and multiply it by Avogadro's number, 6.022 times 10 to the 23rd. And if we crunch those numbers, we get the value 96485 with the units of coulombs per mole. This is an important constant called Faraday's constant, and we use this to calculate electric charge using the equation Q equals N times F. Notice how N would be in moles, typically the number of moles of electrons, and F is in coulombs per mole. So dimensional analysis says that Q would be in units of charge, coulombs. So we're in good shape. So let's use that information to answer this question. If the weight of copper in this reaction decreased by 0.0635 grams, how much charge was transferred? Let's take a quick look at the equation that we were talking about here. Notice how we have copper, that the weight is going to decrease and forming copper 2 plus. It is going to be important for us to pay attention to the stoichiometry here in terms of the number of electrons. Notice how copper 0 is oxidized to copper 2 plus, so 2 electrons are transferred. So that will come up in our stoichiometry in just a minute. Let's start off with 0.0635 grams of copper. We want to convert that into moles. 1 mole weighs 63.5 grams. Now that's moles of copper, and we want to convert this into moles of electrons for our equation. And we saw that there are 2 moles of electrons transferred for each 1 mole of copper. So we take a quick look. Our moles of copper cancel out, our grams cancel out, and we are left with moles of electrons, and that number 0.02 moles. Now we can take that and plug it into our equation for electric charge. Multiplying it by 96485, which is Faraday's constant, and when we crunch these numbers, we get 1.93 times 10 to the 3rd coulombs. So this is one of the basic concepts that we need to be familiar with. The next concept that's important Next concept that's important that we want to discuss today is electric current. Current is simply the charge that flows per unit time. The units of charge, again, are going to be coulombs, and typically we use seconds for the time, because then coulombs per second is also an amp. We now have the information that we need to answer questions such as the following. What current must pass through a solution in order for the constant rate of copper dissolution to be 6.35 milligrams? The solution in this case is still the silver nitrate in which a piece of copper has been added. We want a current, therefore the answer must be in amps or coulombs per second, and the information that we're given is 6.35 milligrams per hour. So we need to perform some dimensional analysis to convert this number into the units that we want. So if we start off with 6.35 milligrams of copper per hour, let's first get rid of the milligrams. And we know that 1 milligram is equal to 10 to the minus third grams. There we go. Then let's convert our grams into moles. And we know that 1 mole of copper weighs 63.5 grams. And recall that we need moles of electrons, not moles of copper. And again, from our equation, we saw that 2 moles of electrons are transferred for each 1 mole of copper. Let's go ahead and chug these numbers here. We end up getting 0.002 moles of electrons. Per hour. If we take a look at the units that get canceled, everything gets canceled except for moles of electrons and hours. So we still need a little bit of work. We need to convert the moles of electrons into coulombs, and we need to convert the hours into seconds. 0.002. I'm just going to rewrite what I wrote up on the top. Let's first convert the hours into seconds. 1 hour has 3,600 seconds. And how do we convert moles of electrons into coulombs? This is Faraday's constant right here. If we say 96485, take a close look at the units. They are coulombs per mole. That's moles of electrons, so the moles cancel out, the hours cancel out. What we're left with is coulombs per second. We crunch this number, we get 0.0536 coulombs per second, and that's the same thing as saying 53.6 milliamps. 53.6 milliamps of current would be passing. So when 53.6 milliamps of current are passing under these conditions, we are losing copper at a rate of 6.35 milligrams per hour. So there are only a couple other things that in the first part of our electrochemistry tutorial that I would like you to figure out on your own. We'll call this left for you. First one is work. We learn that work is related to both potential and charge. It's the product of work and charge. And this is going to lead us to an important relationship between E and delta G. And I would like you to pay close attention to that into your reading. There is also Ohm's law, which we have discussed in the past, where the potential is proportional to current that transfers, and the proportionality constant is the resistance. And then the last one that I want you to pay attention to is power. The general equation for power, which we use the abbreviation or the symbol P, is the product of potential times current. Power is written typically in units of watts. And so I would like you to look at these last three items on your own in the first section of your textbook. Now this sheet that I've just created here will be available as a PDF on our internal website.